Chapter 7 is all about the central limit theorem. So we have a few chapter objectives here that we're going to go through. First is just to recognize when the central limit theorem applies. When are we dealing with a central limit theorem problem? We want to classify continuous word problems according to their distributions, and then we want to apply the central limit theorem in two different cases, one for means and one for sums. The central limit theorem itself is probably the most important thing that we talk about. In terms of its significance mathematically and its usefulness for all different areas where statistics may be applied. So the key is we have a population with a mean of mu and a standard deviation of sigma, and we're taking a bunch of samples of size n. Okay, and n can be it can vary, but if the population that we're dealing with does not have a normal distribution, then we really need to make sure that n is sufficiently large. Okay, the rule of thumb is it needs to be at least 30. But if the population is very, very skewed, then we may need more than 30. But 30 is kind of a good rule of thumb. But if we satisfy those conditions, okay, we have mean mu, standard deviation sigma, and a bunch of samples of the same size, then the means of those samples will follow a bell shape and follow a normal distribution. So if you took the means from a bunch of samples and you created a histogram, that histogram would be bell-shaped. Same applies to the sums of the samples. Okay, in some cases it may be more useful to deal with means. In other cases it may be more useful to deal with the sums of the samples. So you take samples and you just add all of the values together. That histogram will also be bell-shaped, and the sums will follow a normal distribution. So in section 1 we're going to talk about the central limit theorem as it applies to sample means. So quickly to review a few terms, random variable is a single numerical value determined by chance for an outcome of a procedure. A probability distribution is either a graph, a table, or a formula that gives us the probability for each value of a random variable. And then this, I have this under the review section, but I'm not sure we've mentioned this term before. The sampling distribution of the mean is the probability distribution of sample means with all samples having the same size, okay, which usually we call n. So what this is saying is a population may have a particular distribution. So I'm going to say you're talking about shoe sizes. Okay, the probability distribution for shoe sizes will be something. We talked about it may be in a lot of populations normally distributed, okay, but it didn't have to be. But if we collected a bunch of samples and found the mean shoe size, okay, and then we plotted out the histogram for the mean shoe size, it would have its own probability distribution. So what we're going to discover here with the central limit theorem is that those sample means tend to follow a normal distribution even if the population doesn't. So here are our givens. This is just the central limit theorem written in a little more technical language. Okay, we have a random variable x, mean of mu, standard deviation sigma. We have simple random samples, all of the same size n. And what we conclude is the distribution of sample means, which is x bar, remember sample mean is x bar, will, as your sample size gets larger, approach a normal distribution. So if you have a sufficiently large sample size and you take a bunch of samples, even if the population is not normally distributed, the sample means will be. And furthermore, if you were to take all the possible samples of size n, the mean of all of those sample means will equal the population mean. Okay, now we have a new term that we need to know when we're talking about the central limit theorem, and that's called the standard error. Specifically here, the standard error of the mean. This is the most common standard error. There's also a standard error for sums that we'll see later. But the standard error for the mean is the standard deviation sigma divided by the square root of the sample size. Okay, this is a pretty important thing because this is the only part of our z-score formula where things are going to change. You're going to need this part for the z-score formula, so pay close attention to that. And once again, these three conclusions are true even if the population is not normally distributed. So a little piece of notation here. if we're talking about the mean of all the sample means, we throw a new little notation in there, mu sub x bar. Your book uses, in place of just mu, in a lot of cases, your textbook uses mu sub x. Don't confuse that with mu sub x bar. Okay, mu sub x is just the regular mu. They're just putting a little bit of a new name on it because we're dealing with the central limit theorem. But mu x is just mu. Mu x bar is the mean of the sample means. Okay, so just kind of be aware of that slight notational difference that you might see. All right, so when we're applying the central limit theorem to a problem, say we're trying to find probability or something, this is the z-score formula that we want to use. It's slightly different than what we used before. Okay, z equals x bar minus mu. So this is the sample mean, the particular sample mean for some sample that we took of size n, minus the population mean. And all of that is divided by the standard error of the mean, okay, sigma over the square root of n. And just as a little side note, when you have fractions inside of fractions, sometimes we tend to make mistakes in the calculator when we do division. So please be very careful to put that bottom fraction in parentheses when you're doing calculations in the calculator so that you don't accidentally divide by the wrong thing. Alright, so for our first example, engineers making motorcycle helmets have to consider the breadths of male heads. I don't know why, but that word is just kind of funny to me, and so it's in there as many times as I could fit it. Men have head breadths with a mean of 6 inches and a standard deviation of 1 inch. So the breadth is like just another word for the width. So breadth. Part A asks, if one male is randomly selected, find the probability that his head breadth is less than 6.2 inches. So I want to point out that this is not a central limit theorem question because it is not talking about a sample of size n. It's talking about one individual. So I'm going to skip ahead to the next slide and walk through example A. Okay, so in a nutshell, what we're being asked for is the probability that x is less than 6.2. So this is a chapter 6 question basically. So we take 6.2 minus 6 divided by the standard deviation, which was 1, and we get 0.2. I'm going to show you as we go through these little snippets of the table that I showed you in chapter 6, and we'll get our probabilities from there instead of me trying to do the document camera where you can see my screen on the calculator. That doesn't always seem to work very well, so we'll use the table. But from this, you can see we're looking for 0.20, so we have a probability of 0.57926. For part B, now we're going to deal with a sample of 100 adult men. Okay, they've run a production run of 100 helmets. They want to sample 100 men, and we want to see, is the mean less than 6.2 inches. So in part B, now we're dealing with x bar. Okay, notice it's not x is less than 6.2, it's x bar is less than 6.2. So now this is a central limit theorem question. So we're going to use our new z-score formula that has the standard error in the bottom. So 6.2 minus 6 divided by 1.0, standard deviation, divided by the square root of our sample size, which was 100. This gives us a z-score of 2.0. So if we go to the table, we see that 2.00 is 0.97725. So this is our probability for the mean head breadth being less than 6.2. In part C, the production manager sees the result from part B and reasons that all helmets should be made for men with head breadths less than 6.2 inches because they would fit all but a few men. What is wrong with that reasoning? Well, the problem here is that this company is not going to sell helmets to samples of 100 people. They're going to sell helmets to individuals. So what matters more in this case is that the individual has a high probability of fitting this helmet, not that the mean of a sample of 100 fits the helmet. So just because the central limit theorem is important and applicable in a lot of cases doesn't mean it's always the right answer to every question. So this example I like because it kind of gives us an idea of when it's important to think about the central limit theorem, and that is when you're dealing with cases where you have samples of a particular size over and over and over again. So fitting motorcycle helmets is not a good example of that. Those are purchased one at a time by one person, and they need it to fit them. For example number 2, we're going to look at the idea of passenger or boat capacities for passengers according to the U.S. Coast Guard. So there's a story here about a boat called the Ethan Allen, which sank on Lake George in New York, and that incident led the Coast Guard to consider changing capacities for boats. So what they typically based it on is an average weight for the number of passengers that are allowed to be on the boat. So suppose we have a boat that has a capacity of 20 or 3,500 pounds, okay, whichever. So since men are typically heavier than women, we'll assume a worst case scenario that all the passengers are men, and men have a mean weight of 172 pounds and a standard deviation of 29 pounds. So what we want to find out in part A is the probability that an individual man has a weight greater than 175. So in case it's probably not obvious here, if we have 20 passengers all that weigh 175 pounds, that will put us at the 3,500 pound capacity for the boat. So we don't want to ever go over that 3,500 pound number. So if all the men on the boat weigh more than 175 pounds, then we have a problem. So part A, though, we just want to know what's the probability that an individual man weighs more than 175 pounds. So we start with finding the z-score for 175, and that gives us a z-score of, sorry about that, that was my phone. It gives you a z-score of 0.10. And so going to the table again, we see that that gives us a probability of 0.53983. However, this is not a less than question, this is a greater than question. So we need to do 1 minus that, and that gives us a probability of 0.46017. So the probability that an individual man will weigh more than 175 pounds is 0.46. For part B, we want to know what's the probability that in a sample of 20 randomly selected men that the mean weight will be greater than 175. Okay, so now we're back into the central limit theorem for means case, so we're going to change our z-score formula. Okay, so now that we're dealing with the probability that x bar is greater than 175, we use the central limit theorem, which changes our standard deviation in the bottom into the standard error. It gives us a z-score of 0.46. Going to the table, you can't see the 0.4 part of it, but you can see the 0.06 here. But this is the value that we're looking for, 0.67724. And again, because we're dealing with a greater than, we need to subtract 1 minus that, which gives us a probability of 0.32276. So the last thing to consider here on example number 2 is, should the Coast Guard change the standard so that fewer passengers are allowed on the boat? And basically what we need to consider is, what is the probability, or maybe a different way of saying it would be, what's the percentage of samples of size 20 that are going to weigh more than 3,500 pounds? That's basically the same question that we just answered in part B. If the mean is over 175, then the total is over 3,500. So it looked like about 32% of the time that boat would be too heavy. Okay, assuming all the passengers were men. It is still a worst case scenario. But 32% of the time seems pretty high to me when we're talking about, potentially deadly situations where boats are capsizing. So this would be a good example of when the central limit theorem is relevant, because we're talking about samples of 20 people, right? If 20 people get on the boat at a time, then what matters is that mean, not the values for individuals anymore. So the first example with the helmets was a good reason to use the individual z-score formula. This example with the tour boat is a good example of when we should use the central limit theorem formula, because samples are more relevant than individuals. Just a reminder here, the rare event rule, we've talked about it before, but I'm just trying to keep it in front of you. If under a given assumption the probability of a particular observed event is exceptionally small, we conclude that the assumption is probably not correct. So we're still not quite ready to apply this with hypothesis testing, but we're getting really close now. So I want to just keep this rare event rule in front of you. Suggested homework for this section would be practice problems 1 through 6 and homework questions 63 and 65. If you have any questions, please feel free to let me know.